So there's a neat trick that you can do if you have a region that's defined by some sort of parallelogram. If you have two parallel lines and two other parallel lines cutting into each other. And that's this whole thing here. So if I have this region, ax plus by is L1, ax plus by is L2, so those are limit 1 and limit 2. Cx plus dy is limit 3, cx plus dy is limit 4. Then if I want to say u is ax plus by and v is cx plus dy, and by the way, if you do that with these, your upper and lower limits are just these values. So you have the new limits after that using these substitutions. Then the way that you could back solve to get solving for x and y to get the functions you'll need for your Jacobian result in this. Or you might prefer to write like this. This is a little cleaner. X is d over ad minus bcu minus b over ad minus bcv. So notice that all of these have ad minus bc over it. And this is just it. So whatever's a, b, c, and d up here, just plug in here and you automatically get it. And you might say, well, why in the world do we even care about that? Why didn't we just start here? Why do we have to go through the whole thing? Well, there's a couple of reasons. One is that in the case where you don't have a linear substitution, you have some sort of kind of arbitrary arc that you're trying to transform the region of, you're not going to get that. So you're going to have to be a little more careful. Two, it doesn't scale well to 3 dimensions. Technically, there are ways to do it for like some sort of parallelepiped for 3D, but it's kind of nice to have a shorthand for 2D. And you might ask yourself, why does this work? Well, it goes back to linear algebra, or even if you did some matrix math, maybe in high school or something, it's this idea. If u is ax plus by and v is cx plus dy, then we can represent that relationship with this matrix equation. ABCD times xy equals uv. And if you remember how matrices multiply, row times column equals that. So ax times by is equal to u. Cx times dy is equal to v. But 2x2 matrices have a really neat property that you can find their inverse super easy, assuming it exists. And in this particular case, you can assume it exists because if it didn't exist, that parallelogram that you're defining your region as would just collapse into a single line, and that would be very easy to see. So let's assume for a moment that this is not 0 on the bottom. By getting the inverse here, it's just 1 over the determinant times, you flip these two variables, a and d, and then you negate b and c. So you end up with a matrix that's very similar to this. And if we multiplied both sides by that inverse, so if we multiplied that side over here by its inverse, this collapses, so we're left with xy. And if we multiply this side by that on the left, you get that here, and you get that in front. So ultimately, what you get, x and y, are that constant out front, du minus bv, negative cu plus av. So this right here will get you the substitution you want. Now, of course, when you do the Jacobian, you're going to have to still take those partial derivatives, and there's ways to do that too. You could continue to do this because this is formulaic. You could find the generic Jacobian as well and always be able to transform this with no problem. So feel free to do that, but that's kind of beyond the scope of what I wanted to discuss here. This is just a neat little trick to keep in your pocket to maybe make your life a little easier.